This is lesson 63 of the Quantum Mechanics, a mini lecture series titled Eigenstates, part 1. Suppose we have some operator O acting on some state psi, okay, such that the following is satisfied. The following condition is satisfied. In other words, you've got some input here giving you this output here. Okay, so you get psi back, but with something attached to it, okay? This alpha here is a complex number. It's a complex number. Okay, and this psi here, this ket is known as an eigenstate, okay, or an eigenket of the operator O. And it's got an associated eigenvalue, alpha, the complex number, that's the eigenvalue. Okay, and it's derived from the German word eigen, translating to special or unique. Okay, so the word eigen means, loosely speaking, special or unique, right? It's a German word. And eigenvalues, they're a special set of numbers that pertain to a specific matrix. Okay, and in general, it's found that an operator O can have no eigenstates or one or more eigenstates, which may be real or complex. I should say with real or complex eigenvalues associated with them. And if it's Hermitian, if the operator is Hermitian, then the eigenvalues are all real. Okay, Hermitian operators have real eigenvalues. Okay, real because they're things that you can measure in the lab, right? Something is measurable if it's got real eigenstates, eigenvalues, I should say. So when you measure stuff in the lab, properties of the quantum system, what you're really doing is you're looking at the eigenvalues. You're measuring the eigenvalues. And eigenvectors belonging to different eigenvalues are said to be orthogonal, right? I.e. multiplying their respective components and adding them up gives 0. That's what orthogonal means. So let's take, for example, illustrate this with an example. The following. Operator O acting on two different eigenstates where alpha and beta, these two things here are complex numbers, taking them to be complex. We find that basically inner product of phi and psi is 0, provided that alpha is not equal to beta. Okay, and the eigenstates can be what's called normalized to unity. In other words, 1. So we find that this is the case. This case is satisfied. If you take the inner product of each eigenstate with itself, you'll get 1. Okay, in other words, eigenstates are normalized to unity. Okay, unity means 1. Okay, that's what these two conditions mean here. And the set of eigenstates of a Hermitian operator forms what's called a complete orthonormal set. Okay, an orthonormal set is one whose vectors are all of unit length. Okay, they've got unit length, in other words, length 1 unit. Okay, orthonormal set of basis vectors, basis states. And I will show you an example of how to determine eigenvalues and eigenvectors of simple matrices in the next video. But for now, this is what eigenvalues and eigenstates look like when written out like this, when an operator acts on some state, psi, or phi in this case. And these are just some of the properties that you find with eigenstates.